Well, hello everyone. Hello Tech Doyo. My name is Rodrigo, Rod, and I'm gonna be here with you today to talk about one thing that I'm really passionate about, which is maps. And for tonight, tonight here, early morning for you there, I chose this topic, maps in your pocket, and I titled it "The Convergence of Technologies, Needs, and Human Behavior." So why are we gonna talk about maps? Well, when Shaima invited me, she told me that I can talk about something that I really enjoy and something that I can give you some perspective of how I see maps, especially now that with these location-based services and digital maps, there's a truly revolution going on. And yeah, and maps is something that I have been passionate about since I was a kid in geography classes, and then later on buying maps of whatever thing I found. I was collecting them. I have a big collection and books and whatnot. And I always like to explore places. Now with these new technologies, it's a very different way. And I thought that it would be interesting for you to talk broadly about all the pieces that connects maps in the way we use them today or nowadays. So I need to anticipate that this will be like an overview of many things. I will try to keep it as short as possible, but I really wanted to give you a broad perspective of things that probably are very familiar, but connecting them with those that you are probably not that familiar with. And it will be an introduction if later on we want to go in depth into one specific aspect of them, like be sure that I will be more than happy to share that with you. So an overview of what we're going to have today. We're going to have a super brief history on maps. Then we're going to talk about navigation, especially the space-based satellite navigation systems. Then a little bit about software and databases. Then smartphones, which are an important item that we use nowadays, like in a daily basis. And we will review some of the applications, some examples. So let's talk about maps in history, and really it will be super brief. Well, I wanted to include you the first map that humankind knows about. This is the world map as the Mesopotamian saw it. So this one is, as you can see, more than 8,000 years old, and that's what actually portrays what the Mesopotamians thought were the 7 regions of the world, and in the center, their city, Babylon. As you can see, well, this is a very old piece, but this is considered the first map that we know about as a map. This is like going forward some 5,500 years later. This is a map of Mexico City. Actually, Mexico City back then was called Tenochtitlan. So when the Europeans came and they saw the city, at that time that was the largest city in the world, they got back with the drawings that they make, and this was printed in Germany in 1524. And well, nowadays, 500 years later, there's no lake. There's just like a small remnant of what was like a whole valley with a lake. So maps, I wanted to say that they are changing continuously. This is probably a little bit more familiar with you. 130 years later, this was a map of Hindustan at the time of the Mughal Empire made by James Rennell. And what I've read about him is that he is considered the father of cartography in that side of the world. So probably you may have heard about it, or probably this map is familiar to you. 100 years later, like maps got more detailed, and they were used for wars, for territories, for trade. This is an example of how detailed they were at the end of the 19th century, and this one basically portrays different areas in London where what they wanted to know how the poverty was distributed, and at that time, like that, people wanted to do something about it. Then moving forward, another 100 years, this is like a map, that type of map that we all use, or we at least have seen. Probably now with the smartphones, they are not that convenient, probably limited in information, but that's a pocket map, and with the telephone, that's what we are replacing. Moving forward to the latest development, this is the most comprehensive and complete, actually a system that you can use in your desktop. And what this itself, since they started, it's 14, 15, almost 15 years old now. It started being developed by Keyhole, a company here in Silicon Valley. In 2004, Google acquired that company, and they rebranded it to Google Earth. So as a quick summary, you can see just thinking about 2,000 years, how the political map of the world has changed, and how the political boundaries of the countries have changed as well. So that was a brief history. As you can see, like, maps is not something new. They have been with us for a long time, especially because they are very useful as a reference to understand and to explain the world around us. So now let's change to a topic that is also related, which is space-based satellite navigation systems. So having our Earth, many years ago, when people were sailing from one continent to the other, it was necessary to understand where they were and how far they were from the destinations. So they started, I mean, it was easy to navigate around a port where you can see the lighthouse, but as soon as the lighthouse was beyond the horizon, then some problems arose, and people for many centuries, they didn't go further than just the shores. Eventually, there was some development and some advancements in technologies in which, by following the stars and having maps of the stars, they were able to know on what latitude they were, although the longitude was a little bit more difficult. So this is nowadays, when we have a latitude and longitude reference map, this is more or less how this is designed. So you see that this is a 0, 0. It goes on the equator. The Earth is divided in 360 degrees. You have 180 for the west, 180 degrees for the east, and from the equator to both of the poles, you have only 90 degrees, and you create the references of any single square centimeter in the surface of Earth. So with that, probably I want to ask you if you know where this is. This is pretty much how nearly every single point in the surface of the Earth is represented. It can be either with the format of degrees and minutes and seconds, or just transform them into the decimal version. By the way, this place, if you look for it, it's a point, a square centimeter, somewhere in the center of Bangladesh, if you want to check it out later. There are several satellite navigation systems. Probably the most common one is GPS, and it's because it was the first one. There's a story behind it. Probably you remember that the Russians, they created the first artificial satellite that went on orbit, namely the Sputnik. And the Americans, they were worried about what the Russians were doing back then with that satellite. So probably you might also remember that there was well, that was the area of the Cold War, just a few years later after the World War, in which the two superpowers of the world, they were very careful of what the other was doing. And yeah, the Americans, they wanted to know what that satellite was. So actually they created a system to know exactly where on space was that satellite. And then they decided, well, probably if we just use it in a reverse wave, probably we can put satellites on the orbit and then understand where they are, and with that information probably figure out where on Earth can someone be located. So GPS is the American constellation of satellites. There's another one called GLONASS, which is the Russian, with about 24 satellites right now. Galileo is the satellite constellation for the Europeans. They own that. India has also its own, Japan's as well, and Beidou. Beidou is the Chinese. Most of the satellites on this for this application for GPS or for global positioning, they orbit around the Earth. There are just a few satellites that are actually stationary, that they stay in one fixed spot continuously, and they rotate at the same speed as Earth. As I mentioned, this is like a very broad topic. We can, if you're interested, we can discuss a little bit more on another time, or I can send you more information for your research. And this is how, from the perspective of the moon, let's say, this is how the satellites are distributed in specific orbits and moving around 20,000 kilometers per hour. That's their speed in average, and they are many kilometers away. So how do they work? How can I, by having such a like a machine going so fast around me, how can I get to know, well, where I am? Well, for that, you basically need a GPS receiver. How do I know how does that system works? Well, if you have a GPS receiver, they are designed to get the signal of the satellite. Each satellite is transmitting information down to the Earth. And by collecting that information, it's actually giving you the position in a given moment of that specific satellite. And what your GPS receiver basically, in a very simple way, it's calculating or decoding that information, collecting it with a few other samples from other satellites, and then estimating where on Earth you are. You can imagine that this sometimes may not work if you don't have enough satellites on what they call the direct line of sight. That means that your GPS receiver is actually receiving them. Or it can also be that some satellites, they are on the other side of the Earth, so you won't get the signals from them. So there were many problems that they needed to solve, and that's why they have GPS or is intended to have 50 satellites, and then some of them get old, they need to be replaced, stuff like that. So it's a very, very good system, but it's sensible to have like a good reception and that everything is working good at the same time. I'm going to talk now about assisted GPS, which is the way in which we can solve part of that problem. So in this example, you have the person in a position, and with the GPS receiver, it's getting a GPS signal directly from the satellite. But sometimes you don't have continuously connected your GPS so that it's collecting signals continuously. So what it does, it gets assisted, and basically what it does is like in the cellular network antennas, they put a GPS there as well, and it's actually a very cool and good idea because those antennas, they don't move. They are not like uh, like like us, that we are moving around, going from one place to another, giving so much trouble to the GPS receiver to collect signals. So if the signal goes directly to the antenna, or to the GPS of the antenna, and that all that calculation that needs to be done to know where the satellite is can be processed in a computer in the base of the antenna, and then all those calculations transmitted to the phone of, or the mobile phone of the person, or the GPS receiver of the person, then the process can be much faster. That's why if you use a GPS receiver from a smartphone in an urban area, like in a city, you are taking advantage of all that antennas who are processing that data, and you get the position faster. But if you are in a, let's say, on the wilds, hiking somewhere in a mountain, well, on those places you won't have the help of a cellular antenna, or antenna that is collecting GPS signals, and you will need to rely on only GPS. So if you have a good line of sight for each satellite, or the 8 minimum that you need, then you will get your position very fast. In case you have only 1 or 2 available satellites in one given time, it's not a problem. Actually, they have also solved that problem. But what will happen is that it will take longer to get the exact location, because what happens is that each satellite is sending the information of its own, but also, or additionally, also the information of where the other satellites are around. So you can imagine the amount of data that requires. But eventually, like if you are patient, you will get all that data and get your position using GPS. There's another one that normally we use to estimate our location, which is cellular networks. You are familiar with this because most of you have used a mobile. Now it's probably a few years ago, there were many people in the world that were not having them, but now in very remote and rural areas of the whole world, it's actually cheaper to put cellular networks rather than making cables to put landlines. So the way it works is also with antennas. You have one antenna covering certain area, and if you want to get your location, it's just a matter of triangulating your position with the antennas that are around you. We can go more in detail on another day, but I think you are very familiar with this. And another one on city that it's important that helps you locate yourself is the Wi-Fi footprints. So in this example, imagine that you have in one of those rooms of that building, you have a Wi-Fi connection. And that Wi-Fi connection will spread around it the signal so that devices can get connected to the internet in this case. And as you see, there are some areas that are green, some other areas that are yellow, and some others that are red or actually invisible. So the invisible means that because of the walls or the other building, the signal won't be reaching that place. So it will be stronger on the green area, and that will be the coverage where you will have the Wi-Fi very well connected. And each of these Wi-Fi connections have a footprint. So what companies like Apple, Google, those, they know, or they somehow are aware of those Wi-Fi connections, and just by knowing in a given position how strong one signal from a specific Wi-Fi router is, and you get like all of those, it can give a very approximate estimate of where that device is located. Probably you have noticed when you turn off your location-based services or your GPS on your phones, sometimes it tells you if you enable Wi-Fi, then it will be more accurate. Of course, the more you use, you can actually use all those references to estimate your location on any place on Earth. If they're available, the more you use, the more precise will be your specific location at a given point. And that's the magic behind it. I'm putting this because once I got a question of why the blue dot. It's normally in the digital maps, your location is represented by a blue dot. And my guess is because the Earth is blue and they got inspired on it, because you might remember that the blue dot looks like that. It's pretty much similar to the Earth. And in history, it was said that when this picture was first taken, it was, it was such a big deal for humanity back then that they started calling Earth the blue dot where we live. So that's my guess. Now let's move on to software and databases. Let's talk a little bit more. We have already one component, which is the navigation part, the estimate of where on Earth you are based on satellites and Wi-Fi connections, cellular towers. So now let's talk a little bit about software and databases. So a question for you would be, if you want to know where you are, what is easier to understand? A typical database with the address on one of the fields, or actually a map with certain references that can be drawn, in this case like markers. I think all of us would agree that probably the one on the right side, it's much easier to understand if we are talking about places and location. Well, if we want to represent all the information in a place, we need to have a map. And I'm putting this one because this is actually the projection of the land mass that exists on Earth that we typically use on a digital map. And there are some reasons for that. We will talk a little bit about them. But one thing that I want you to remember is that this is a representation, but which actually works very well, or it's actually very useful for computers, because you can have the scale like pretty straightforward. But just before we go into that detail, like the problem with this projection is that it doesn't show, or it distortions the real areas of the countries. So you may remember that this is the Mercator projection, and basically imagine that you put a piece of paper around a sphere, and then you put a light bulb, turn it on, and it will, the shadow that it projects is actually the countries. But as you can see here in the bottom side of the slide, if you have a person, just to have like another reference, if you have a person on each of those places, when they get projected, they get distortion. So even though they would be the same height and the same type and everything, like the ones on the equator normally tend to be of the correct size. But then as you go towards the North Pole and South Pole, the distortion is bigger. And I'm going to go back because then that explains why countries or like Russia are much bigger than they actually are. But if you think that Africa is actually 3 times bigger than what it appears, then we have to take that into consideration. One thing about every single map that you will ever see in front of you is that the map is biased by the perspective of the one who creates it. So if you see a digital map, all of them are using this projection because it's pretty easy to determine scales. If you want to zoom in or zoom out, it's very easy to just zoom on something that can be orthogonal or squared, and then you just put the same size for your reference square or for your unit square, and then you can go zoom in and zoom out as many times as you want. But you will need to make additional considerations if you want to get the real geometry of a road, for example, or of a boundary, or any feature that you may have on the map. If that one is pretty easy to solve, once you have the algorithm, it will be the same for all of them. But just remember that even though we will get in the future very familiar with this map, it actually has this defect, so to say. And one more thing of why it's like a reference like that, it's so easy, is because we can use this Cartesian plane and put reference and create points for features or roads or polygons. Now, I'm going to move a little bit forward. If you want to put all the information that exists in the real world on a digital map, then you will need to think about layers of information. In this example, or in this representation, you have a layer for imagery, a layer for elevation, a layer for the network of your roads and metro lines, public transportation, etc. You may have another one for addresses. And addresses, remember that they work differently everywhere in the world. It's actually one of the main challenges for all the maps is to actually make a human readable and understandable reference to where a user might be if they choose a square, let's say, in the map. If I give you a lat long, as I did it before, probably all that many numbers might be difficult to remember. And if you change one of them, it actually, in real world, may represent the other side of the world, or probably 200 meters away from where you are. So we need to be very, very precise. And at the same time, you need to give your users the understanding that they may get more familiar or understand better a simple address than a set of complex and long numbers. So GIS, which stands for Geographic Information System, is actually a collection of all those components that you see there. On one hand, it's software to process all that data. It's data that it can be in different formats. There you will see that we have vector data, raster data, image data, and attribute data. And it's basically depending on what you have, or if you want to scale something. For example, if you have a feature of boundary of, let's say, a city, if you are gonna zoom in and zoom out to see it in from a different, let's say, level of how can I explain that? So if you want to see it like related to one country, probably you will have it at a level where you can see all the cities that conform that country. But then if you are not that interested on the country, but still want to have the reference, you will need to zoom out to cover bigger area. And then that same location that probably was visible at zoom 1, when you zoom out, if it's vector data, it will move accordingly. And you won't have like, imagine if you don't use it that way, and you have, let's say, an image of just a picture. If you zoom out, the picture will be very small that you won't see it. And if it's so big, it will get pixelated. So it's better to use vector data there. There's also methods like procedures of how you're gonna use that data, create that data, and more importantly, maintain that data. There's also the component of people, like all that people that will be making decisions. Some of them will be collecting the data, and you want to have you want to have them well trained because it's expensive to get all that data and process all that data. That you want to make sure that it's being done according to the methods that you have been put in place, and also hardware. The more geospatial data we use, the more hardware we need to process, to store it, and to process that information. And let me just go back because I wanted to include that for this imagery, like we collect these satellite images from the space just as a GPS, but the satellites that are used for that are, of course, carrying cameras that would take pictures like this one. And I included for your reference later when you see this this presentation, I included here a video, and this is one of the worldwide providers of satellite imagery in the world. So many of the main maps, digital maps that are out there, they use this. Well, this is one of the providers, and I can tell you that I have seen the video, and this World View 3 satellite that was launched last year in September, October, if I remember well. It's amazing the capacity that it has, and also the resolution that those images have. It's you can recognize an object that it's 30 centimeters long. So if you put a bucket in the middle of the road and the picture is taken, in that aerial imagery or satellite imagery, you will be able to recognize it. And probably it could be more precise, but there are like some regulations, and at least the US, the one that it's ahead probably in all these kind of technologies, it only allows a resolution of 30 centimeters maximum. It's a big deal because not long ago it was 50 centimeters, but if we go just 15 years earlier, GPS systems have deliberately an error of 100 and 200 meters, that even though the satellites for the military they were working perfectly, civil usage or GPS applications by civilians were restricted and of course not working that well, because if you add that deliberate error of 100 and 200 meters plus the natural error that a GPS signal has, then it didn't make any sense, that blue dot. So we needed to go, there are several things that need to be happen in parallel in order to make things to work the way they are. So with that background, let's discuss or present a little bit some information about smartphones. So smartphones, we have had them for almost 30 years now. At the beginning, they were big and super costly. Like the usage was extremely expensive. But there's a law there, the Moore's law, in which basically it says that the capacity of chips and information systems and storage is actually doubling every year, and it has been happening like that for the last 20. They say that it's going to be the end very soon, because now it's so much advanced that we still don't have like that applications to take advantage of that, and there are some limits also to the physics and chemistry of the components that make that possible. Let's see. But what has happened so far is that the computer inside of those smartphones is it's making computer power to be more powerful in a smaller device. And well, a phone is a miracle of engineering. It has just cameras, sensors of all types, batteries that can give you energy to use your phone for up to a week now, and it will continue to be like that. Among all those little chips and components, there's a GPS. And to give you an idea of how a GPS looks like, well, that's pretty much the type of GPS that almost every single smartphone nowadays has. The cost has been reduced to $1.50. When GPS was used by the military, you need an equipment and carried with two people, and probably that equipment was $500,000. So you see that there has been progress. But also one thing to keep in mind is that GPS, it's, I mean, quite awesome, but it's not as precise as like to give you precision of inches. And the reason for that is because, well, the satellite signals are very weak, and the antennas that telephones uses is actually enclosed into the device. But if you want a very precise GPS, I promise that I will send you a cool video of what they use in the there's a competition of sailboats called America's Cup, and those ones have a satellite system. And actually for the race, Jerry, I think she has seen it. They measure everything with GPS and satellites, and they know exactly who got first and who is behind who with the accuracy of millimeters. They are amazing. But those GPSs, they cost $100,000 each, the GPS receiver. So with $1.50, it's really amazing what we can do now. So putting in perspective some characteristics of how the smartphones have evolved. Well, here you can see a graph of the computer speed that several types of processors have. And this is interesting that when we went to the moon, the equipments and the computers that we used that had used that speed. And now if you have an iPhone, or if you have seen an iPhone of the old days, like already the versions of 3 years ago, those devices have more than 10 times the power that the computers that were used to put the man on the moon. This is the Moore's law on processing power that I was mentioning to you. In 1981, it was well, close to zero, but well, this is like not accurate because you cannot see properly the scale. But the scale is more appreciated since 2003, and you see how it's going up. And then another perspective of how many smartphones are there in the world. Well, here we have information from the first quarter of 2007. So you see that, well, besides the fact that there's a specific operating system that is more common than any others, you can see the amount of phones that are being sold on every quarter. And it's not that, I mean, if you have a phone I have a phone that is already 3 years old, and it's still working, and it's still being used. So this is only the sales, but just consider that all those numbers are accumulated through time. Okay. Well, I have to discuss or to show some of these apps or maps working on a smartphone, just some characteristics of them. Um, there's one specific map, Google Maps, who actually has another very neat feature that takes pictures from the world with cars like this or with trackers like that, where you don't have access with a car. You use that called tracker, and it's just like a camera that takes spherical pictures, and to place them on the map, they have also a GPS. We will see some maps in a second. I just want to mention that one important topic now with the convergence of these technologies, having a GPS in your phone, having a phone that has enough computer power to process information, and having a digital map on it, then there are location-based services that many companies, startups, or other companies are, I mean, not necessarily startups, but basically the location where you are is more relevant lately. So companies try to take advantage of that. And there are some neat applications that I want to also show as soon as we finish with the presentation. Um, some, like, probably you are familiar with Twitter or Waze. Some others that are just recently launched, like Tomnot, that brings crowdsourcing of geospatial data by taking advantage of the distribution of data and the volunteering of people all over the world. And probably also Lyft and Uber are interesting. And I'm not familiar if in Dhaka Uber is already there. I hope not, because it's a very aggressive, some of the strategies that they have. So they need to settle down a little bit of how in places where some type of transportation it's more typical, and probably they don't need technology, just like the Jitishas, the Girishas that you have in Bangladesh. It wouldn't be nice if they have Uber, I believe, but that's only my personal opinion. And well, hotpads, I will show you some of them. And so just to finish the presentation, we have GPS on one hand, we have smartphones on the other, we have software and databases to process all that tons of information that geospatial data creates, and the need of humans, it's right where all those three circles get together. Those are the places in which if we use properly all these technologies, we can create apps and we can create services that actually solve needs and problems in humanity.